What do you get when you take the curl of a vector field? No, it's not a joke. There's no more joking in this class. What do you get when you take a curl of a vector field? Not a conservative. It's the amount of rotation. But the answer I was going for was a vector field. So when you take the curl of a vector field, you get another vector field. And if you look at each point, where you see those arrows and how they rotate describes, with the right-hand rule, describes another arrow, essentially, right? And so that defines a new vector field. So for us, it would make sense to take the integral of that vector field. Curl of a curl, it's probably 0. I don't know. But in terms of conservative vector fields, if you take the curl of a vector field and you get 0, then that vector field is conservative. Okay. So we have issues with that. So this next section relates the flux integral with a, what's this on the other side? Can you tell? It's a line integral. Okay, so our notation is a little bit different. We use little s instead of little r. And and sometimes we use that triangle for the curl. So S is a surface. Now they say piecewise smooth, which means it's smooth piecewise. It could be a bunch of surfaces put together. As long as each piece is smooth, then the connection where they get together may not necessarily be smooth. So S is an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary with a positive orientation. So C has a positive orientation. F is a vector field with components having continuous partial derivatives on the region that contains the surface. Then this is Stokes Theorem. Stokes Theorem will hold. So what does that mean? I don't know what that means. Let's just make it up. So let's say you have a surface S, and S has to have a boundary, right? And S also needs an orientation, and so we can orient S going inward or outward, it doesn't matter. But what would matter is that the orientation we assign to S will generally follow an orientation that we'll need to assign to the boundary of S. So you can already tell, I hope, that this is the boundary, right? So we left the surface S open with a boundary. And suppose we give it this orientation that's pointing outward. Then what does that mean for C to have a positive orientation? So here's one way to look at it. For each of these normal vectors on the curve on the surface, imagine using your right-hand rule and imagine a specific rotation that this has with your right hand. As those normal vectors get closer and closer to the edge, they're going to push this curve to have a specific orientation. So if we take a look at this vector, for example, with the right-hand rule orientation, if you get that closer and closer to to this curve, it's going to essentially push your curve to have this specific orientation. What? Where? Right here? Right here? At the center of the curve?
Yeah.
No, we don't want the center of the curve.
No, I know, but if you got closer, it's still going counterclockwise. You know, it looks like you push over the vectors, the directions are counterclockwise, and you just moved in a clockwise direction. Yeah, on the curve.
Well, we're not looking at curl yet. We're relating S and C right now. So nothing to do with a curl yet. S has a specific orientation. When you get closer to the edge, it's going to push your boundary, which is a curve, towards a specific orientation. I don't know if I want to use the word clockwise or counterclockwise when we're talking about this, because the orientation of these things can look kind of different. I guess if we take a look at a simpler surface, like, say, a cone with an outward orientation. So this is a cone with an outward orientation. If I follow through with a right-hand rule, which way my orientation is going to go, when I get closer and closer to the top here, it's going to push my orientation in this direction.
You don't want to go in the same direction, like in terms of like the path at which it's rotating. You're talking about like gears, how they move in the same.
Yeah.
Oh, okay.
Well, not like gears. Maybe like gears. Because the gears will turn the other way, right, when you put gears together.
Yep.
It's not quite how gears work.
Gears don't move like that. They move together. Okay. Then maybe the opposite.
So it pushes whatever, if you look at it as a gear, whichever way this is going to get pushed. Okay? So C with a positive orientation refers to the orientation of the surface itself. Okay? Now, if we take that same surface, this cone, and instead have our vectors, our normal vectors, to be pointing inward, I guess this should be going up a little bit. And then with the right-hand rule, this is inside of the cone. With the right-hand rule, you're rotating in whatever direction that is. When you get to the edge, it's going to push your curve to move in this direction. Okay? So that's the first important thing to get from Stokes Theorem, is the orientation of C. Orientation of C depends on the orientation of S, and you can tell the orientation of C by following those normal vectors from S. Okay? Well, if it doesn't have a positive orientation, now what does that mean? So the orientation is almost arbitrary. Somebody can just say, I want this orientation for the cone to go inward or outward. Doesn't matter. And then based on that, you're going to parameterize your curve with that specific orientation. Now, if your curve, let's say we're looking at this example over here, your curve, if you can't, for some reason, if you can't parameterize your curve going in this specific direction, and the only way you can do it is to make it go the other way, then you can still use that parameterization. Just remember that's an orientation reversing parameterization, and throw a negative sign when you do your integral. So it doesn't matter how your orientation, how you parameterize your surface or your curve. Orientation is not necessarily going to matter in the work that you do, because if you have an orientation that goes the opposite of what you want, then just throw a negative sign in your answer. Although in the quiz I specifically asked you to find a parameterization that gave that specific orientation. So we'll see how that went. All right, so that's the first part. And the first part is relating your S, your surface, with your boundary C. And I think we've already mentioned that sometimes, just so this can be more related to each other, we use the partial of D, which is not called the partial of D. So whenever you see this partial notation next to a geometric object, you're going to assume that that's the boundary. That's the boundary, I'm sorry, not D, S. Okay? So that's the first part. The second part is that your surface integral has a curl, and then your line integral has the original function. So that leads me to say that the integral of a derivative, a curl is some form of derivative of a function over a surface, is equal to one less integral of the original function evaluated at its boundary. So this is another form of the fundamental theorem of calculus. Okay? So sometimes we see this Stokes theorem written in whatever order. So it's a curl. This is another way to write the curl. And then they put ds. Sometimes they use dot n with a ds with the s not a vector. But I like this notation with a ds, so I'll keep that. Is equal to now the line integral over the curve, which is a boundary of S. And since the boundary of S should be a closed curve, think about that. If you have any surface that has an opening, the boundary is a closed curve. And sometimes I like to use an arrow going in a counterclockwise direction to say that this C has a positive orientation of F dot, and our notation is d little s with an arrow on it. So you're switching from a surface integral to a line integral in most cases. Sometimes a line integral is so difficult for some reason a surface integral might be easier. So we can do that also. But this is now one of these equations or one of these theorems where you have an equality. If you're given a line integral, it might be easier to do a surface integral, or if you're given a surface integral, a flux integral, then it might be easier to do a line integral. And it depends on the problem. Okay? All right, that's Stokes. Let's, usually the thing to do is to verify Stokes theorem given a problem, so that's what we'll do, and we'll see how far we can get with that. So I'll pick a problem from the book. We have a vector field, y, comma, z, comma, x, and your surface is the hemisphere. With y bigger than 0, so, and then they give the orientation positive y-axis. Oh, I don't know. So according to Stokes theorem, there's two sides to this, and we want to verify Stokes theorem. So we want to check both sides to see if it's true. The first thing we want to do is we want to get a sketch of how this surface might look like and identify the curve C, the boundary of that surface. We got the sphere x squared plus y squared plus z squared is equal to 1, and this gets chopped off when y is bigger than or equal to 0. So this is your surface. Now, the orientation that we want for this is in the positive y-axis, so we want our orientation going like this. Which means as we get closer and closer, this is hard to see. As we get closer and closer to the boundary, we are looking at this circle going in which direction? Down in the front. Okay? So if we were to parameterize this, this is for the line integral. We parameterize this curve going in this direction. And for the surface integral, we parameterize the surface with this outward normal. So those are our values. Now we need to either look at the line integral or the flux, or the line integral looks at the original function, and then the flux looks at the curl of that function. So let's do the curl while we're here before we get started. Curl of f So imagine there's a partial with respect to x, with respect to y, and with respect to z up on top here, and then we'll do the curl. So in the x component, there's the derivative of this function, x with respect to y is 0. The derivative of z with respect to z is 1. So we get a negative 1. Now in the y component, it's going to be a negative. The derivative of x with respect to x is also negative 1. And then with respect to z, the derivative of x with respect to z and y minus y with respect to y is negative 1 also. So it turns out that the curl is a nice, easy function to deal with. That's good news. Okay. So let's parameterize stuff. Let's do the line integral. Let's work on the line integral first. So to work on the line integral, we need to parameterize the curve, this curve over here, x, y, and z. And what can you say about this parameterization of x, y, and z? We use t, we can use theta, doesn't matter, let's use t. Is there an easy one that I can fill in here between the x, y, and the z? Which one? The y is 0 because this is not moving out of the xz plane, so the y is going to be equal to 0. And now you're just parameterizing a circle of radius 1, so between the x and the z, you just throw in a cosine and a sine. Except we have to worry about the orientation, right? So right now, let's put cosine t for the first one and sine t for the second one. Cosine t for x and sine t for z. And then what we can do is we can figure out what happens. Imagine which way this thing moves as we go from 0 to 2 pi. So let's say when t is equal to 0, where x is equal to 1, and z is equal to 0. So I'm right here when t is equal to 0. When t is equal to 1, no, let's try pi over 2. When t is equal to pi over 2, cosine of pi over 2 is 0, and sine of pi over 2 is positive 1. So it looks like my orientation takes me, when t is equal to 0 from here, to t is equal to pi over 2 up there. So it looks like I'm going the other way. So I could do one of two things. I can switch these two to get a positive orientation, or if I decide I want to keep this orientation, I just remind myself that this is an orientation reversing parameterization, and then I'll throw in a negative sign at the end. Okay? That's what I'll do. You can do it any way you want. That's what I'm going to do. So, we have our stuff for the line integral. So we're all set to compute the line integral. And we have a vector field, y, z, x. We want to dot it with our r prime. Let me just put r prime here. So remember that this is a ds in line integrals. And so now I want to drop the x's and the y's and the z's. So let's actually compute this now. The y is 0, the z is sine t, and the x is cosine t. I want to dot that with the derivative of my parameterization. The derivative of cosine is negative sine. Oh, I have another 0 that goes away when I take the dot product, and then the derivative of sine is cosine. And then now I know I'm going to go from 0 to 2 pi. Say it again? Oh yeah, the negative 1 from our orientation reversing parameterization. So you dot them, the first components are gone, the second components are gone. I have a cosine squared, 0 to 2 pi cosine squared t dt with a negative 1 out in front, and that's something I'm not interested in computing by hand. So let's put the minus 1 in front. And our integral goes from 0 to 2 pi. And we have the cosine of t squared dt, negative pi. So that is one side of your Stokes theorem. This is the line integral side. Okay. So now let's do the other parameterization. There are several ways to do this. One way is to parameterize using phis and thetas in spherical coordinates. But I think I'll take it in steps. I'll parameterize it like it was like an x and a y first, and then change that over to spherical if I need to, when I need to, if I need to. If it's an if, because it's a double integral, so it's not going to go to 3 dimensions. All right. So my parameterization for this will just be the regular graph parameterization. X is equal to x. Y is equal to the square root of, if I solve for y here, 1 minus x squared minus z squared. And then my z is just going to be z. And I have to figure out how the orientation is going to go here. So my domain here is unit circle. on the xz plane. I'll put less than or equal to here because it's the filled in unit circle. And then now I want to take the derivative of this parameterization, which I'll call phi, and see which way my normal vector is pointing. So my phi of x is the derivative with respect to x, which is 1 comma whatever that is. I think it's negative 2x over the square root of 1 minus x squared minus z squared. Right? It's like 1/2 power, you subtract 1 and blah, blah, blah. And then the derivative of z with respect to x is just that, is 0. So the phi with respect to z is 0, essentially the same thing, except you switch variables. And depending on how we cross it, in this case we're going to cross it like this. We'll do x and then z. We'll see if the y is pointing in the right direction, the correct direction. So with respect to x, it is the derivative with respect to x, it's negative 2x over that whole thing. With respect to y, it's negative 1. Oh boy, opposite again, so let's just fix that later on. We'll fix that with a negative sign. But my y is that negative 1 business, so my orientation for this is reversing. And then my z is going to be negative 2z over the square root of 1 minus x squared minus z squared. Okay, so let's make a note that this is ORP. And then we'll just throw a negative sign in front of our integral. So our integral is a surface integral that we're integrating over the surface. And we take our curl, not the original function, but the curl vector field, minus 1, minus 1, minus 1. And we're going to dot it with this cross product, dx dy. I'll say dA. I suppose if I'm doing that, I should call this d already, because I need to integrate over that domain. So we're integrating over this domain. Let's simplify this a little bit. Negative 1 times this integral. And I have a negative 1, so it's basically this thing turned positive and then added up all together. So that is 2x over this minus x squared minus z squared plus 1 plus 2z squared of x squared minus 1 minus x squared minus z squared. And then I'll say dz dx, or dx dz. So I think now is a time where I probably want to go to polar coordinates, where I would, or I can just integrate this in my Wolfram Alpha Mathematica. But if you want, you can change this to polar coordinates. So x is equal to r cosine theta, y is equal to r sine theta, and then work it out that way. What? Well, the limits would be, if I don't go to polar coordinates, the limits would be this circle. So that would be, if I integrate with respect to z first, it would be a negative square root of 1 minus x squared, positive 1 minus x squared. That's the bottom and top half of the circle. And then the x goes from minus 1 to 1. So that would be my limits if I didn't go to polar. Now, if I decide to go to polar now, then my limits would be easier, and assuming that this thing would also look a little nicer. So let me just do it like that since I have Mathematica and I can integrate whatever I want. Let's see what happens. So we have a negative 1, and then the integral from minus 1 to 1 of another integral from minus the square root of 1 minus x squared to positive. And then my big, ugly looking function would be 2x divided by the square root of 1 minus x squared minus z squared plus 1 plus the same thing with a z. Switch the order there. And then I'll integrate with respect to z first and then x. And I hope I get pi or negative pi. So there you go. Now, you probably wouldn't want to do it this way. You would much rather change it to polar coordinates because you'll have nicer integrals to deal with. But this works out fine. So this is your resulting integral here. Okay, so now it's verified. So tomorrow, I think what we'll do is we'll take a look at problems where it would be easier. We use Stokes Theorem, and it would be easy to compute the flux of a curl. Or if you're trying to find the flux of a curl, it might be easier to compute the original, the line integral instead. So we'll take a look at those different types of functions. Okay, there's one more big theorem after this. That's the Divergence Theorem. So we may take a peek at that next time also. All right, see you guys tomorrow.